everyone, my name is Zhadi Zhang. Our paper proposes an abstraction-based training method for robust image classifiers. For abstraction, all perturbed images are mapped into intervals before feeding into neural networks for training. By training on intervals, all the perturbed images that are mapped to the same interval are classified as the same label. Consequently, our approach significantly improves the robustness of trained models. For the abstraction, our training method also enables a black box verification approach, which is scalable to arbitrary types of neural networks. We evaluate our method on a wide range of benchmarks. The experimental results show that our method outperforms state-of-the-art. Acting as classifiers, neural networks have been adopted in a variety of applications, such as pattern recognition. It is a growing trend that embedding them in safety-critical systems, such as self-driving. However, neural networks are found to be vulnerable against the robustness and may suffer from adversarial attacks. For example, a Tesla car in autopilot mode caused a fatal crash, as it failed to detect a white train against a bright sky with white clouds. Therefore, applications in safety-critical domains demand high reliability guarantees. Among them, robustness is one of the most important properties, which requires neural networks to make the same classification for all perturbed inputs in a reasonable perturbation range. There has been a considerable amount of work on training robust neural networks against adversarial perturbations. Conventional deep-learning approaches augment the training set with adversarial examples. They target only specific adversaries, depending on how the adversarial samples are generated, but they cannot provide robustness guarantees. Recent approaches attempt to train certifiably robust models with guarantees. They rely on the robustness verification results of networks in the training process. However, there are mainly three obstacles for these approaches to be widely adopted. Firstly, adding the verification results to the loss function for training brings limited improvement to the robustness due to overestimation introduced in the verification phase. Secondly, they are time-consuming due to the high complexity of the verification problem. And finally, the verification is tied to specific types of networks in terms of network architectures and activation functions. To overcome the above obstacles, we propose a novel abstraction-based approach for training verified robust image classifications. Our approach mainly includes three parts: training process, verification process, and refinement process. Next, I will introduce the three parts separately. The first is abstraction-based training method. For traditional training methods, each pixel of an image corresponds to each neuron in the input layer. After perturbing the image, each pixel corresponds to a perturbation interval, and we first map the perturbation interval to abstract interval. The purpose is to ensure that the network classifiers images mapped to the same abstract interval at the same label, thereby assigning the impact of perturbation on the classification results, and then improving the robustness of the image classifier. In order to ensure the uniqueness of the mapping, we define the following mapping rules. Firstly, if an abstract interval contains the perturbation interval, the perturbation interval will be mapped to the abstract interval. Secondly, if the perturbation interval has an intersection with two abstract intervals unequally, the perturbation interval will be mapped to the abstract interval with the larger coverage area. Finally, if the perturbation interval has an intersection with two abstract intervals equally, the perturbation interval will be mapped to the abstract interval with a larger value. In order to input the abstract interval into the network, input the maximum and minimum values of the abstract interval into the network, and other hyperparameters such as the number of hidden layers are the same as the traditional training method. And for verification part, Thanks to our training method, the verification part only needs to use the simulating function during training to abstract the perturbation interval, and then use the network to directly classify the abstract interval. If the classification result is consistent with that of the original image, then the network satisfies robustness. Otherwise, the network doesn't satisfy robustness. Since the internal architecture of the network doesn't need to be considered, our approach can verify networks of arbitrary architectures. As for refinement, our approach has a hyperparameter abstraction granularity that determines the size of the abstract interval, which in turn also affects the classification accuracy and robustness. Therefore, we propose a gradient descent-based algorithm for refining this hyperparameter. By using the backpropagation algorithm, we can obtain the gradient of neurons in the input layer. If the gradient of the abstract interval indicates that the interval should be longer, then the algorithm would be terminated and output the model. If the gradient of the abstract interval indicates that the interval should be shorter, the abstraction granularity is reduced and the model is trained again using the new abstraction granularity. Then we first evaluate the performance of our approach on ReLU models. The table shows our approach obtains up to 95% improvements than the competitors. As for the accuracy, our method achieves higher accuracy than the competitors for all data sets and models. Regarding training time, our method achieves up to 26 speedup. Regarding the verification overhead, our approach achieves up to 600 speedup. In addition, our approach is applicable to networks with various activity functions such as sigmoid and tanh. Moreover, our method is also scalable with larger models. Finally, we conclude some findings from this work. Our approach outperforms the state-of-the-art or robust training approaches with up to 95% improvement in reducing verified errors. Then our verification algorithm is scalable to larger networks and is applicable to a wide range of networks. While there still exist some problems, such as whether more robust image classification can be trained using more precise abstract domains. Then, secondly, how to balance verified errors and accuracy. Thanks for listening. All the authors' information is listed here. Please feel free to contact us if you have any questions.